Welcome back. In this section, section 1.3.4, we want to describe all subspaces of E2. So that's R2 with the usual vector structure and R3 with their usual vector structure. So our goal is to give a geometric description of all subspaces of E2 and R3. In the last subsection, subsection 1.3.3, we've shown that subspaces and spans are the same geometric object. In linear 1, we had a complete description of all spans in E2 and E3. So putting these two things together, we get a complete description of all subspaces of the Euclidean vector spaces E2 and E3. All right, so let's write them out, but we don't need to prove it. We've already done all the work. There are three types of subspaces of E2. There's one smallest one, the zero subspace, so containing only the zero vector. And then I could have any line. Let's give up. So it's a line through the origin. Oh, sorry, just a bit of a habit to write 3, but in this case we're in R2, so only AB, so through the origin 0, 0. And then the only other thing that we could have is all of E2. So either a line through the origin, 0, or everything. Now in R3 we have one more type, we have 4, we still have the 0 vector, we still have any line, so x, y, z equals t, a, b, c, through the origin 0, 0, 0, and any plane. So for plane, let me use an implicit equation, ax plus by plus cz equals 0. I'm not going to put a d because it is, again, through the origin. So I don't need a point for the lines because that point is 0, and I don't need a d because d is 0. All right, so either the 0 vector and that's it, a line through the origin, a plane through the origin, or all of R3. So in linear 1, to determine what kind of object a span was, we needed to consider whether the set was linearly independent or not. We need to generalize that concept. We'll do so in section 1.4, but for now, let's just remind ourselves of what we did in linear 1. So I want to know what this span is geometrically. I have 3 vectors. I want to know if they give me all of R3, give me a plane, give me a line, or give me the 0 vector. All right, so if you remember, if all the vectors are the 0 vectors, then the span would be just a 0, 1. Clearly not the case. Case number 2, if all the vectors are parallel, but not all 0, then the span is going to be a line. Well, not the case here since 1, 1, 3 isn't parallel to 2, minus 1, 4. In fact, to prove they're not parallel, let me compute the cross product of two of them. I'll compute the cross product of V2 cross V3, and I'll use it in the next bit anyway. So 2 minus 1, 4, cross with 4 minus 1, 11. I'll expand like we did in linear 1 to 2 minus 1, 4 minus 1, and I'm going to take the crosses. All right, so I got minus 11 plus 4, so that's minus 7. 16 minus 22, that's minus 6. Minus 2 plus 4, that's 2. This isn't 0, so they're not all parallel. And so we're not in this case. All right, so we've narrowed it down. It's either going to be a plane or all of R3. To check whether it's a plane, you need to check whether they're coplanar. Then the span would be a plane. And so I'm going to compute V1 dotted with V2 cross V3. So that's going to be the dot product of 1, 1, 3. And the cross product we just computed. So I'm going to get minus 7 minus 6 plus 6. I get minus 7, which isn't 0, so not coplanar. And if they're not coplanar, then they look something like this. I have V2, V3 on their plane, and I have V1 above. And then when they look like this, then the span is the only thing that's left. Span of V1, V2, V3 is all of R3. And so it's E3 as a subspace.